Hello students, today we are going to explain principle of parallel axis or theorem of parallel axis. It can be applied to any object. Means the object may be laminar or it can be defined in three-dimensional space. So for the explanation of this theorem, we consider a diagram which is showing the body of any shape. Here center of mass of the body is denoted by C. Axis passing through the center of mass is denoted by ACB. Here there is another point O. Axis passing through this O is MOP. About this axis also body can rotate. Here the perpendicular distance between them is H. There is a point, say D, at which DM element is there. Distance of this element from this center of mass is CD. Distance from O, it is OD. Now once we know the distances, we can write moment of inertia like this. Moment of inertia of element DM about ACB axis it can be denoted by IC and it is equal to CD square into DM. It is by definition of moment of inertia. Similarly, moment of inertia of DM about MOP axis, it can be denoted by IO and it can be equal to OD square, integration of OD square dm. Again it is by definition. Now here to have the relationship between IO and IC, we have to modify the figure in this way. Here we produce OC and then draw perpendicular from D. Point of intersection is N. Then we can write the expression for IO and simplify it like this. Integration of OD square dm. OD can be equal to dn square or nd square plus on square. Here nd square plus on square and this is multiplied by dm. Integration of nd square plus, now on square can be written as oc plus cn square or cn plus oc square. Cn plus oc whole square. This is the simple geometrical steps here. nd square plus, here cn square, expanding the bracket, cn square plus twice cn into oc plus oc square multiplied by dm. nd square plus cn square, nd square plus cn square is equal to cd square. cd square plus here twice cn into oc plus oc square multiplied by dm. Now here we write the integration in this way. Integration of cd square into dm. First term plus Here twice Cn OC. Here we know OC is equal to H, perpendicular distance between two axes. It is H. We can substitute it as H. 2 into H, and inside the integration it is Cn into dm. Cn into dm plus OC is H square. It can be taken outside the integration because it is constant, and integration of dm. So we have taken integration of each term in the bracket. Now CD square dm is IC. It is the moment of inertia about ACB axis, plus twice H. Here we have to note Cn dm. Integration, here we take one side step. Integration of Cn dm is representing sum of moments about center of mass, and it is equal to 0 by the points which we have discussed for the center of mass. So this term is equal to 0. Now the third term is H square, and integration of dm. Here also we have to know integration of dm. It is equal to mass of body. Here we have to know mass of body is equal to m. It is the total mass. Such elements dm, if we add all these elements, integrate all these elements, then it is m. Now here H square into m. We can write here IO is equal to IC plus MH square. This is the mathematical formula for the theorem of parallel axis. So if we adjust two axes and body can rotate about two axes, here IO and IC are related to each other, and that can be stated like this. Here again I write the step so that we can state the principle or theorem. Here IO is the moment of inertia about any axis passing through O, and IC is the moment of inertia which is about the axis passing through center of mass. Once we have such description for each quantity, then we can state the principle. Here moment of inertia of a body about axis passing through about any axis is equal to the sum of moment of inertia of a body about the axis passing through center of mass and product of mass of body and square of the distance between two axes. This is the statement of parallel axis. Now once we have this statement, we can apply it for number of objects having any shape. So here we have to apply this theorem as well as theorem of parallel perpendicular axis to a simple body which is a ring. So that we can understand again the theorems and revise the theorems. So this is parallel axis theorem, and we have perpendicular axis is also simple relation. Iz is equal to Ix plus Iy. This is for the perpendicular axis. So if we consider the ring as a body, ring can be shown in horizontal plane. Its center of mass can be shown by C. Axis passing through C and perpendicular to the plane of ring can be shown like this. About this axis the ring can rotate, and this axis is own axis of ring. This is the own axis. Own axis we have already discussed that it is the axis passing through the center of mass or center of body and perpendicular to its plane. We have adjusted here the ring in a plane which is the horizontal plane, so that the axis is vertical. Now the first question we have to solve, that we have to know the moment of inertia of ring about its diameter. How can we show the diameters here? In the plane here, this can be a diameter. So this we have shown as y-axis in our previous discussion. Similarly, diameter can be shown along x-axis. For the sake of simplicity, we have taken x and y-axis, and own axis is z-axis. Here Iz is equal to Ic. Means moment of inertia about z-axis. Z-axis is passing through C point. We can take it as Ic, and we have noted that moment of inertia of ring about the axis passing through the center and perpendicular to the plane of ring, it is equal to mr square. So this is the given expression for moment of inertia in case of a ring. We have to determine it about the x-axis or about the y-axis, because x and y-axis here we have represented for diameter. Actually diameter can be represented in any way, but for the sake of simplicity and to apply the theorem of perpendicular axis, we have noted and shown the diameter along y-axis and along x-axis. From the symmetry here, it is Ix can be equal to Iy. Now here we write applying theorem of perpendicular axis. We can write Iz is equal to Ix plus Iy. But here Iz can be taken as Ic. It can be equal to mr square. This we can take here we write is mr square. And one thing we have noted that Ix is equal to Iy by symmetry of figure, because x and y axis are mutually perpendicular, and in the plane of ring we can write mr square is equal to twice Ix, or mr square can be equal to twice Iy. We write Ix is equal to mr square upon 2, Iy is equal to mr square by 2. We can describe here Ix is moment of inertia of ring about x-axis, but x-axis also is parallel to diameter, so we can write it as about diameter. So instead of saying about x-axis, we can say it is about diameter. Moment of inertia about diameter, which is coinciding the x-axis, is mr square by 2. Similarly, moment of inertia about y-axis, it also represents moment of inertia about diameter, which is coinciding to y-axis. It is also mr square by 2. So we have to note or write the answer. Moment of inertia of ring about the diameter, it is equal to mr square upon 2. Now the next axis which we have asked here, moment of inertia of ring about the axis, particular axis, about the axis which is tangential and perpendicular, tangential and perpendicular to plane of ring. So the description is like this, and the solution we can take by considering the theorem of parallel axis. So again we read the description. Moment of inertia of ring about the axis which is tangential but perpendicular to plane of ring. We can show it like this. This axis is passing through O. About this axis also we can rotate. Now here there are two parallel axes. The situation is here we have to now concentrate only on these two parallel axes, and here y-axis and x-axis for some time we have to ignore. So two axes are there and they are separated by the radius. H is the separation between two axes. We write here by considering the theorem of parallel axes. By theorem of parallel axis, IO is equal to IC plus MH square. This is very simple. IO, here mr square is given expression for the ring which we have noted somewhere. Here again I can note here IC is given, it is mr square. Now substituting for the second term, H is equal to R, so we get here IO is equal to twice mr square. This is the moment of inertia about this axis which is tangent to the ring but perpendicular to the plane of ring. Now we here write IO. The answer, it is twice mr square. This is the second question. We have to solve here like this. We have solved already. Now the third one is moment of inertia of ring about the axis the description is again like this, which is tangential and in its plane. The axis is tangential to the ring, and in the plane of ring it can be shown in the diagram like this. About this axis also ring can rotate. This point is denoted by O dash. Now here we have to ignore this Z axis, this axis in the second description. We have to concentrate only on two axes, which first one is Y axis and another we have drawn here. This is O dash and suppose it is P, O dash P axis. For that also we apply the theorem of parallel axis, because two parallel axes are there. By applying theorem of parallel axis we write IO dash. Here dash is used. In the second description we have denoted it by IO. Now for the third one we denote it by IO dash. It is equal to, here IC plus MH square, but we have to clear here that IC in this case is IY, because here the moment of inertia about parallel axis means passing through center of mass, but along y-axis we have to consider, so it can be ICY, we write, means the moment of inertia passing through center of mass but not perpendicular. It is the axis which is parallel to y-axis, or it is coinciding the y-axis here. Here IY we can write IY plus MH square. IY we substitute here as MR square by 2 plus MH square. Here again H is equal to R, MR square, and we get 3 by 2 MR square is the moment of inertia of a ring about the tangent in the plane of ring. So here I can write IO dash is equal to 3 by 2 MR square. So this is the explanation and application of both the principles. Principle of parallel axis and principle of perpendicular axis. In the first description we have used Iz is equal to Ix plus Iy, and in both the next descriptions, for next description we have used theorem of parallel axis. So we can use it for planar body or any shaped body. So today we stop here. Thank you.